Right, so our next inductive proof looks a bit similar to one of the earlier ones we did, but it is again slightly different because there's a couple of different ways you can actually accomplish this one. So we've been asked to show using induction that 2 evenly divides into n squared minus n. So starting off with our base case, we need to show that this holds true for n equals, I'm going to say n equals 2 this time. You can probably figure out why if you substitute n equals 1, but I'm going to let n equals 2 be our base case, and so 2 is 2 divisible by 2 squared minus 2. Yes, it is, because this is 4 minus 2. 2 divides into itself 1 times. Our base case holds true. And now we move on to our inductive step. So once again, with our inductive step, we have to show that this holds true if we replace n with n plus 1, so the next term in this particular step. So we just do a direct substitution, n plus 1 squared minus bracket n plus 1. And if we expand all of this out, we're going to end up with n squared plus 2n plus 1 minus n minus 1 from this term here. And what we can see is that this term and that term are actually common to this bit up here. So if we simplify those out to the front, we can say, because our inductive hypothesis is that this is true, that n squared minus n must be divisible by 2. So we know that this part of the expression is divisible by 2. What we don't know is how the rest of the terms affect that. So if we simplify the rest of these out, we can see that these cancel, and what we're left with is this 2n term. Now, hopefully it's obvious that anything multiplied by 2 will then be divisible by 2, so we know that this remaining term is also divisible by 2, and therefore this remaining expression will also be divisible by 2, and that's the end of our inductive proof.